So in this experiment, we are going to observe voltage, power and current relationship in a single phase RLC circuit. Okay. So as we know, this resistor, inductor and capacitors are the passive components of any electrical circuits, any electrical AC circuit. So you will observe what will be the current and voltage relations and how will be the power of these circuits in this experiment, and you will find out the power factor by doing the you will obtain the power factor by doing the experiment. As you can see here, when the voltage is given to the R load, you can see the voltage and current waveform here. I have written the voltage waveform in black and the current waveform in red. As you can see, the voltage and current are in phase with each other. So as you know, in any circuit, the voltage into V into I is the power of a electrical circuit. So in any instance, the power V will be positive in a resistive circuit. So this V is positive. So if you calculate the average V from this circuit, this will appear somewhere like this in a pure resistive circuit. Okay. So average power will be like this. Okay, when the circuit is pure resistive. So when the circuit is inductive, as you can see here, voltage is leading the current. Voltage is leading the current. At some instance, at this instance, as you can see here, voltage is positive, current is negative. So voltage is positive and current is negative. So the power will be negative. At this instant, power will be negative. So again, at this instance, V into I will be negative. At this instance, voltage is positive and the current is positive. So power will become positive. Okay, power will become positive. So again, at this instance, as you can see here, voltage is negative and the current is positive, and again the current voltage will become, the total power will become negative. This goes on. So as you can see here, if you can see the average power of this circuit, it will be as it is a sinusoidal waveform, the average power of this circuit will be 0. Okay, any pure inductive circuit, the power inductor does not absorb any power. So in this circuit, the average power of this circuit will be 0. Similarly, as you can see here, in a pure capacitive circuit, when the current is positive and the voltage is positive, the power is positive. Similarly, at this instance, voltage is positive and the current is negative, the power will become negative. Similarly, it goes on. So even in a pure capacitive circuit, the power will be 0. So how can we define a power factor? Okay, power factor is a measure of the degree to which a given load matches that of a pure resistance. Okay, so we have a load, we have a RLC load. As you can see in this diagram, we have a RLC load. In this circuit, there will be a power which is active power, there will be a power which is apparent power. Okay, so apparent power, the overall power which is actually absorbed by the load is actually the active power load. The average power given to a load. This average power consists of inductor, capacitor, and the resistor, which will have some degree of freedom, some phase shift from the power, which is the same power which will be absorbed if it is given to a resistive circuit. So power factor can be defined as P load divided by PR. It's actually PR. P load divided by PR, the average power given to a load, and the average power if it is a resistive load. Okay. So in a RLC circuits, you have resistor, you have inductor, and you have capacitor. Okay. When the voltage is applied to this circuit, so there will be an active power, there will be an apparent power. Okay. So the whatever the difference between this active power and the load, this apparent power and the actual power, it will be known as reactive power. The reactive power. Okay, as you can see here, this angle theta is power factor. Okay, so if cos theta is equal to 1, then you can see this will be equal to that of this angle. So the overall power absorbed by the load will be equal to of the resistive value. So how can this happen? See, as you can see here, the voltage of the inductor is leading the circuit, and this is the across the resistor VR. This is the current, this is VL, and this is VC. Okay, so if the voltage across the inductor and voltage across the capacitor are same, they both will cancel each other. So the power factor of the circuit will be unity. So when the power factor is unity, that means the total power of the circuit will be equivalent to that of the power given to an RL load. So in this experiment, you will be having an RLC circuit. So what you will be doing is you will be giving the supply to the RLC circuit. You will be measuring the voltage across each circuit, and you will be obtaining the total power of the circuit, that is P load. Okay, we know that P load is equal to VI cos phi. So VI cos phi. You will be measuring the voltage. You will be measuring the current. Then you can I will write it as cos phi. Then from that you can calculate the power factor cos phi. You will be doing that by using cos phi is equal to P load, whatever the power we will be measuring using the wattmeter, divided by voltage into the current. Okay, this is what we will be doing in this experiment. So you will be observing how the voltage, current, and the power relationship in a RLC circuit will.
In this experiment, we are connecting series RLC circuit and measuring the voltage across resistor, capacitor and inductor in order to draw a phasor diagram. So this is auto transformer. We have connected a wattmeter and we have connected a voltmeter. We have connected a multimeter. In this multimeter, we will be measuring input voltage. We will be measuring voltage across the resistor, voltage across the capacitor, and voltage across the inductor. As you can see here now, the voltage now is at 0 volt. Now I will be slowly increasing the auto transformer in order to increase the voltage. So as you can see in the multimeter, the voltage is increasing. So I have kept the voltage around 100 volts. So now we will be measuring the voltage across resistor. You can see the voltage across the resistor, and we will be measuring the voltage across the capacitor. You can see the voltage across the capacitor. Now we will be measuring the voltage across the inductor. You can see the voltage across the inductor. We also connected an ammeter in order to keep the current below the rated value of the resistor. So from this measured voltages, you can draw the phasor diagram. We have also connected the wattmeter in order to measure the power. So I will be slowly reducing the auto transformer voltage.